Processing a digital image by convolving a filter mask across every pixel in the spatial domain quickly leads to a computational bottleneck. As image resolutions scale quadratically, performing millions of overlapping spatial calculations becomes far too slow for real-time processing systems. To bypass this limitation, engineers map these matrices out of the physical space and entirely into the frequency domain. What requires complex, multi-step convolution in the spatial domain translates into a simple element-by-element multiplication in the frequency domain. This specific mathematical translation relies on a theorem proposed by Jean-Baptiste Joseph Fourier in 1807. Fourier proved any periodically repeating function can be modeled strictly as a weighted sum of sine and cosine waves. By multiplying these pristine waves by specific coefficients and adding them, we exactly reconstruct the jagged, complex signal at the bottom. Mastering how to break down an image into these geometric waveforms is the absolute prerequisite for designing advanced digital filters. To apply Fourier's logic to actual digital images, we first have to formulate it for continuous, non-periodic signals. This equation defines the one-dimensional continuous Fourier transform, explicitly mapping spatial signal f of x into frequency spectrum f of u. Notice the boundaries evaluate the area under the entire curve, stretching from negative to positive infinity. Inside the integral, the complex exponential term acts as a rotational operator, testing the spatial signal against every possible frequency to see which ones match. Calculating these integrals generate transform pairs, demonstrating the duality between spatial shapes and frequency behaviors. On the top row, a hard-edged box function in the spatial domain resolves into a rippling sinc function in the frequency domain. This proves that creating sharp, sudden geometric changes in physical space requires infinite, gradually decaying frequency ripples to accurately construct them. Now compare that to the middle row. A Gaussian distribution in the spatial domain translates perfectly into another Gaussian distribution in the frequency domain. Because the Gaussian curve has a smooth spatial transition, it entirely avoids the severe rippling artifacts produced by the hard edges of the box function. These integral proofs establish the exact geometric rules of frequency mapping. To process photographs, we must adapt these continuous formulas into finite digital systems. Digital images are not infinite continuous waves. They are discrete sequences measured in finite pixels. These sequences have hard boundaries, typically defined from coordinate 0 up to a finite number, m-1. Looking at this equation for the one-dimensional discrete Fourier transform, the continuous integral is replaced entirely by a summation algorithm operating over exactly m points. Running this discrete summation generates complex quantities, splitting the data into a real and imaginary part. To determine the physical amplitude, we calculate the Fourier spectrum, or magnitude. As shown here, it's the square root of the sum of squared real and imaginary components. Below that, the phase spectrum calculates the exact geometric angles between them. If we square the resulting Fourier magnitude, we get the power spectrum. Engineers use this power spectrum to locate precise drops in signal strength, allowing them to define exact cutoff thresholds for low-pass and high-pass filtering. We must account for the spatial to frequency scaling theorem. The top graph shows a discrete box of k points and its spectrum, with amplitude ak over m. Doubling the spatial area below compresses the frequency spread, but doubles the amplitude to 2ak over m. This inverse scaling law is an unbreakable constraint. Whatever you expand in spatial pixels will always compress your frequency bandwidth. To process a complete photograph, we project this one-dimensional logic into 2 dimensions. The single summation formula scales up into a double summation, accounting for a spatial matrix of m rows by n columns. The spatial coordinates x and y directly map to the frequency coordinates u and v in the exponential. Executing this double summation calculates a complete, 2-dimensional Fourier spectrum plane. The exact mathematical origin of this plane, coordinate 0, 0, is the direct current component. It represents the overall average intensity of the entire image. This 2-dimensional transform has a strict periodicity property. The mathematical output repeats itself to infinity, every n steps horizontally and m steps vertically. It also maintains perfect symmetry, meaning the magnitude of the transform is exactly mirrored across the origin. Because of this inherent periodicity, calculating a standard 2-dimensional transform splits the most critical low-frequency data, pushing it out into the 4 extreme corners of the output matrix. To center the spectrum, we multiply the spatial image by -1 to the power of x plus y, shifting the origin perfectly center. Here, low frequencies, smooth gradients, cluster tightly at the origin, while high frequencies, edges and noise, radiate outward into dark space. By drawing geometric masks directly onto this centered frequency plane, engineers can instantly delete specific coordinates to execute complex blurs, sharpening routines, and noise reduction across the entire image. By translating continuous integrals into centered two-dimensional matrices, we establish the complete mathematical architecture required to execute high-performance digital image enhancement.